This work is about reinforcement learning generalization for nonlinear systems through dual-scale homogeneity transformations. The efficiency of load pickup and delivery can be significantly enhanced by utilizing the load swing. It doesn't only speed up the process, but also allows placing loads despite physical limitations that prevent the UAV from hovering over the target position. However, it becomes more challenging when parameters such as the cable length are varied. If there exist some transformations that can guarantee the angle amplitude profile, then we can utilize the first oscillation to bring the load to the goal position. To achieve this, we formally define the dual-scale homogeneity. Consider a nonlinear system in which the state equation is a function of the state and alpha, where alpha is the vector containing j physical parameters of the system. If there exists a time-scaling factor zeta and a coordinate transformation g such that the transform dynamics is a function of a new parameter vector beta, then the systems in 1 and 2 are homogeneous. Note that beta must have a smaller number of parameters than alpha. We call the property in 3 the dual-scale homogeneity since it contains both a scaled time and a scaled amplitude. Since the transform dynamics can be written as in 4, the problem boils down to finding the transformation g which leads to a right-hand side with a smaller number of parameters than the original representation. In the case of a system under control where U is a static map, the original states can be reconstructed given that g is a one-to-one function. Similarly, the transform dynamics can be written as in 7, where U becomes a homogenizing control law. To achieve the dual-scale homogeneity property, we provide theorems for two nonlinear systems showing the required transformations. The homogenizing control laws allow the transformation of the state space representations into other ones in a scaled time and new coordinate systems. The transformed systems are not a function of the eliminated physical parameter, which is the cable length in this case. The method is extremely helpful for learning-based controllers such as reinforcement learning policies, since retraining is not required when the physical parameters of the system change. In the case of online variation of the parameters, recursive least squares can be used. On the other hand, if the variation happens offline, the parameters can be used directly in the transformations as what has been done in the following experiments. In these experiments, the quadrotor swings the load to its target position. Both policies are optimized for 0.5 meter cable length. Yet the superiority of the homogenized policy emerges when tested with cable lengths of 0.75 and 1 meter. Thank you for watching.